So, today we continue to discuss about the MESFET with particular reference to threshold voltage and subthreshold current. In fact, we have discussed the effect of the channel length and also the effect of the spacing between the n plus layer and the gate, that gap. Okay, this is the self-aligned implantation technology, that is a SAINT, where this gap can be adjusted very precisely to the level of 0.2, 0.3 microns of that order, and this is a gate length. So, what we are seeing is the effect of the gate length and this gap on threshold voltage. I will project it once more. So, that is what we saw. We have discussed in detail about this. As you go to shorter gate lengths, threshold voltage gets shifted to the negative side because of the two dimensional effects which are coming in. In addition to the field in the vertical direction, you got the field in the lateral direction also along the channel. That prevents the channel being blocked completely with a particular gate voltage. You must apply more negative voltage, okay. And that becomes more and more predominant if the gap between the n plus layer and the gate, that is smaller, because then the channel length becomes smaller, fields becomes higher. So, the two dimensional effect becomes much more dominant. So, because of that, the 0.15 micron is rather dangerous to use, and 0.3 micron is more acceptable, and you can overcome this problem further if you actually increase the field in the vertical direction compared to the lateral field. You can increase the field in the vertical direction by increasing the doping accompanied by reduction in thickness, so that pinch off voltage or the threshold voltage remains the same thing. Now, one more aspect which is very popularly discussed in the case of MOSFET, which is common for all the field effect transistors, is the subthreshold current or subthreshold conduction. What you can just keep this slide here. What I am pointing out here is, normally when we do VGS versus ID, when you take, okay, you have got 0 and then that is a characteristic which we call it as threshold voltage. This is an enhancement mode type of device. Threshold voltage is positive, gate voltage you must apply positive voltage, so that the device you can just turn off. Now, we call this as the square law right from the threshold voltage, just when the channel is pinched off. Now, it is what actually in reality what happens is, when you go right up to threshold voltage, still it is not completely off. So, what we are taking a look at is this region around threshold voltage, particularly what voltage which go below that, how it is turning off. For example, what we understand from this curve initially is, when you take a look at a casual look at this curve, what we see is you go to threshold voltage, current is 0, but current cannot go turn off to 0. There is certain finite current flowing, it may have come down to microamperes or several microamperes. You must reduce the voltage further down, so that current is reduced down to at least 1 or 2 orders of magnitude. Now, if you take a depletion type of device, that is the characteristics. You have got threshold voltage here, this is negative. Okay. Now, I apply voltage which is below the threshold. So, that is actually around this point, how will the characteristics be? In fact, we can have one short discussion for both enhancement type and depletion type. Only difference is threshold voltage positive here, is negative here. So, here if I want to go below threshold voltage, I must have VGS which is less than threshold voltage, but positive. If I want to go below threshold voltage, I must have VGS more negative compared to threshold voltage. Okay? That is the whole thing that we are discussing. So, what you can see here is in this plot, which is actually an experimental result which people have reported in the papers for SAINT FET, self-aligned structures. There are different curves you can see, quite frightening to see, because you can see on the x axis you have got the VGS, the same curve that we are putting, and on the y axis you have logarithm of ID. It is not ID, it is not a linear region that we are seeing. So, if you see in the log scale, I come down below threshold voltage, it is almost linear. Linearly falling in the log scale means actually the characteristics exponentially falling. So, you would like ideally once you come below, you reduce the voltage below the gate voltage, you would expect it to fall down very steeply. That means it could turn off. But you can see there is a curve here from the threshold voltage, it is falling very gradually. That means, if I want to reduce the current by at least 2 to 3 orders of magnitude, I have to reduce the voltage from 0 right up to minus 3 volts, very large voltage. That is not a good sign. So, these things have been observed for the plots are given here for different gate length. The gate length varied from 1.3 micron, this curve, 0.9 micron, second curve, 0.5 micron here, 0.1 micron. This is about the range that they got. So, they have put some number of curves with the range, okay. But you can take it as one curve if you are putting an average value. So, you have got 1.3 micron here, the gap between the gate and the N plus region is 0.15 micron. You are cutting it very sharp. So, for those devices it is like this. In fact, you are talking of a really short channel effect. Now, first on the first hand, before we understand why it is not steeply falling in this as to reduce the channel length or gate length, before that what we have to understand is this like this when the long channel device is present? How will it fall? Okay. I will keep this curve, we will go through the analysis, then we can understand this. So, these devices were for channel width equal to 5 micron and spacing between the N plus and the gate layer is 0.15 micron. Okay. So, these devices were for this type of device. Okay. Just put it like this, N plus, I am just augmenting the whole curve, the same FET, then the N plus, okay. And then you have got N layer. I have metal here, drain, I have the metal here, source, and I have this gate here. So, that is the gate. So, all that is done in that plot is this is varied, kept on reducing, keeping this width same, which would mean this is shrunk and this is also shrunk. So, that the gap is same. To find out how this VGS versus IDS, ID is there when voltages, this is N layer, for voltages below the threshold voltage. And this is semi-insulating. Let me keep that graph there, that figure there, so that we can take a look at it whenever we need. First, what we are trying to do is, let us not worry about short channel 1 micron, 2 micron, a long channel, there is a gate which is very long. Okay. In that situation, how will be the behavior of the device below threshold voltage? Okay. So, what we see is long channel device, that is what we see first. There, if I plot the potential, I call this as y and I call this as x. Okay. So, I will just put this back here. This is A. It is getting a bit crowded, but still I think you can figure out, see those things: channel thickness, y direction, x direction. What we want to do is, at pinch off or when VGS is equal to VTN, for both case, whether enhancement or depletion type, when VGS is equal to VTN, if you take the depletion layer, how will that be? Let me just plot it right here. I will take a long channel device. Okay. So, when I take VGS equal to VTN, what is the meaning of that? The meaning is the depletion layer has closed at the source end. So, depletion layer actually is like this. This is the N layer. Okay. Depletion layer actually has closed here, and if VDS equal to 0, it will be like that. So, depletion layer actually will be, if it moved like that, almost like that. That is the depletion layer edge. Okay. Now, the potential actually is negative here with respect to that total drop. So, the potential, the applied voltage between this and this is VTN. Okay. What is the potential variation from here to here? If I plot equipotential lines, this is the maximum edge of the depletion layer. If I plot another depletion layer at a lower voltage, it will be coming like this. So, I can have all the depletion layer like this starting from 0 position. Okay. In fact, it is a solution to the Poisson's equation. Equipotential lines will be going like this, and here it will be like this. This is not a very difficult concept. So, what you are telling now is, if I move along this line from the source end to the drain end, there is no potential variation. If you move at the edge of this depletion layer, there is no potential variation. Please understand this very carefully. Okay. If there is no potential variation, that is where we take that current is 0. If there were potential variation, current would have been there if some charge is there. But when you go to the edge of the depletion layer, what is the charge concentration? We take it as 0. But you can see from here to here there is no potential variation. What is the carrier concentration here? The carrier concentration here is equal to N naught or N 0 equal to N d. The carrier concentration at this edge here is N 0, if I want to call it, that is equal to doping. Okay. What is the carrier concentration here? Same. So, if I do not apply any voltage, there is definitely no current, neither concentration gradient nor electric field. But if I apply voltage here, okay, when I apply voltage here, if it is a long channel device, there is no potential variation here, because it is a one dimensional effect. If there is apply voltage, it may go from here to this side like this, depletion layer may move that side, but between this point and this point there is no potential variation. Okay. But when I apply a potential like this is plus, this is minus, this is plus, that is minus. Drain I am making positive, the entire voltage is appearing across that, there is no potential change here, okay, because whole thing is depleted there, and there is no, if it were short channel it would have extended, but because long channel all that is happening is the depletion layer widens here. What happens to carrier concentration here? Plus minus. Whatever carrier concentration is here will be there, that will be brought down to 0, like a reverse biased p-n junction. Electrons are actually collected completely by that. So, it will not, okay. There is a potential drop from here to here. So, carrier concentration will be much lower than the carrier concentration here. Here the carrier concentration corresponding to what doping is there. Okay. Here the carrier concentration is low. Now, of course, the area for cross section will be very, very small. It is a small layer which is conducting there. Okay. So, carrier concentration is equal to doping concentration here, here it is 0. So, what will you say now? There is no field here, there is no potential drop, but there is a concentration gradient. N d here, 0 there. So, between these two, there will be a concentration gradient, there is a current flow. So, what will happen now will be x 0 x equal to L g, okay. This is L g. This is almost similar to MOSFET, but the mechanism is different here, way the pinch off taking place. So, this is 0 carrier concentration. I plot n as a function of x, electron concentration that is falling from there. So, when at Vt at Vg is equal to Vtn, there is a concentration gradient. How much is the current would depend upon how much is the area of our cross section. Area of cross section is very small, so that is a very thin layer, maybe a couple of dBi lengths corresponding to kT by q into 2 or something like that, very small voltage, very small thickness. So, current density may be there, but current will be small. So, the ID in this case will be J d will be equal to q dn minus q dn dn by dfx. dn by dx will be same everywhere. There is no change in slope, there is no recombination. So, whatever slope, that is why it is linear. So, it will be just equal to this concentration by that 0. So, the current actually at threshold will be equal to what you are talking of, threshold will be J drain will be equal to q dn n d divided by L g. Why? That is n 0. This quantity is n d equal to n 0 or n 0. Just put it separately. I call this as n 0. Okay. So, then I will put it here again once more. This is n 0 divided by that length, that is the dn by dfx. Okay, that minus sign gets cancelled with the thing because the slope is negative. So, this will be equal to q dn n d by L g. So, what we are telling is there is some amount of current density giving rise to current at threshold. In fact, people talk of threshold, okay, it is at 5 microampere is the threshold, and the drain current drops down to 5 microamperes, that is the threshold. That is one way of identifying. That means that 5 microampere is there. Now, from 5 microamperes, how it will fall down if we come below the Vtn. That is what we are trying to see. So, here I have got some of the terms. For example, what we talk of now is sub threshold, that is a voltage that you apply to the gate which is below threshold voltage. So, let us see what happens. I will remove some of these things now, so that you can see it better. All these are long channel devices, what we are talking of. I will put it once again. So, Vg S is equal to Vtn minus V. That is the second case. First case was when Vg is equal to Vtn, that is what you got. Second case is when Vg is equal to less than Vtn. Now, you can see it works out fine for you for both enhancement and depletion mode, because Vg is less than Vtn. If Vtn is 1 volt, Vg is 1 volt minus whatever we apply. and the V that we talk of here are not in volts, okay, 100 millivolts, 200 millivolts, or we may sometimes talk of even higher voltages. So, this is 1 volt, and if this is 0.5 volts, I am talking of 0.5 volts. In other words, just to put a diagram here, if it is positive there, that is VTN. If that is VTN, we are talking of the point here. What is the current there? So, we now estimated this, what is the current is this one. Doping concentration decides that. Okay. I want to go down to this point. In the depletion mode type of device, how does it work out? VTN is negative. It is negative, minus 1 volt, let us say, minus 1 volt again further. So, if this is minus 1 threshold voltage, okay, I have been using sometimes VTN, VTH actually. This is, if this is minus 1, minus 0.5 volts, minus 1.5 volts, you are going down here. So, please understand the same formula, same discussion holds good for both enhancement type and depletion type. Let us plot the depletion layer for one particular case, because whole same thing holds good. You can understand from here that the equation that we have used is similar to the equation of a bipolar transistor. In the base region, you have got in the NPN transistor, you have got electron concentration raised up, electron concentration 0, the whole thing is by diffusion. Same thing that we have written here. Now, all that we have to find is, if I reduce the voltage VGS below VTN, what will be this concentration at this edge? That is what we want to see. Let us see what happens. Let me plot that potential, only the potential variation. Okay. Let me just plot that a better line. This is the 0 line, 0 voltage. Supposing I say at the source end, I think I better draw, I think I can remove this thing now, because I need more space here. I will put this here. So, what we have now is, we are talking a long channel device. So, it is like this, and we have got the source, we have got the drain, and we have got VGS, and we applied some VDS. So, at threshold we had this behavior, corresponding to that it has pinched off. That is, if VDS equals 0, now it is like that. So, what we are seeing is between this point LG and this point 0, that is x, that is what we wrote. Now, if I apply Vg, which is less than, okay, if I apply Vg s equal to Vtn minus V, let us talk of depletion mode, because argument holds good for both. More negative voltage you apply to the gate, what happens? What happens to this depletion layer? It will expand that way. Okay. So, this will be like this. This is for this situation, the edge of the depletion layer. And what will be the concentration here? Here it is ND. What we want to see is what is the concentration here. That concentration has fallen down because there is a drop from here to here by an amount equal to V, because VGS is VTN here corresponding to that depletion layer. Now, if I have VGS minus V, more reverse bias, depletion layer has moved here. So, change in the voltage between this point and this point is equal to that. Okay. So, now what will happen will be, if you do that, just few things I had sorted it out, because there is a lot of confusion on this. So, now N naught, or I can plot this particular potential now. X equal to 0, okay, and x equal to L. If I see, if I take this as 0 potential here, how the potential varies along this line? We are talking along this line only, because there is no current here, because charges are very small there. As you move from here to here, see, this is the edge of the depletion layer. As you move from the edge towards this deeper into depletion layer, what happens to carrier concentrations? Way down to 0. So, what we are talking of is a very thin layer, Debye length there, how much is the charge? And we have to worry about that, because we will be still having microamperes of current. You may not worry about one device, let us say it is microampere, 1 microampere, half a microampere, why should I worry? If in the integrated circuits, if there are hundreds of such devices which you believe it is off, all those currents add up, there is power dissipation. So, that is why you want them to turn off really, when they turn off, they really turn off with very low voltage difference. So, now here what will be the potential difference? 0. At this point it is negative, that is at x equals 0. So, from here onwards I have a drop like this, that is V. Okay. This quantity is V. It is very simple, but one has to really follow carefully. And from here onwards up to this point, what is happening? No potential change. Okay. That is corresponding to this potential. See, this one will actually come depletion layer like this, but I am plotting from here to here, and on the channel what is the carrier concentration I am finding, that from there to drain there is no potential change. So, you get that thing like this. Previous case this barrier was not there, this was carrier concentration here, then that is 0 there. So, from this point onwards, how does it go? If drain voltage was 0, that would have come down to plus minus, plus minus, minus plus. But because the drain voltage is there, so you have got, if drain voltage is 0, there is a drop here, plus to minus, and when you come down to this point, if this is not there, depletion layer would have been here. What will be the potential here? Plus minus, minus plus, 0. So, it would have come down like this, but you have got additional drop VDS. So, the whole thing will be like this. You do not have to worry about this at all. So, this quantity is VDS and this quantity is V. So, total drop here from here to this point is VDS plus V, which actually make it further 0. It may move slightly into that, into this channel region, but we are not taking that movement at all, because we are talking of long channel. So, whatever movement is there is small compared to this long channel gate length, that is what we are taking. If you channel length becomes smaller, then you will have to see how much it will move. I will do only qualitatively. This one quantitatively you can get. So, what is the carrier concentration here now? So, if I plot now n of x versus x, that is 0 there, and here it is some n 0, same expression, the drain current is that, only difference is n 0 in this case is smaller compared to what it was. N 0 is smaller because there is a depletion layer from here to here. So, carrier concentration here will be the carrier concentration here multiplied by V to the power minus V by V t. The potential difference is V. So, okay, in this situation therefore, we can write n 0 will be equal to n 0 e to the power of minus V by V t. When you move from positive to the negative or 0 to negative potential, it is a potential barrier to the electrons. This is, I am plotting electrostatic potential. If you take the potential for the electrons, it finds it difficult to move towards the negative charge, negative portion. So, that is why that carrier concentration will be lower by that amount equal to voltage. This is Boltzmann law. So, now what is this quantity V? V is that. You know, this is so straightforward now. So, this is actually equal to minus V is equal to VGS minus VTN. So, the NN 0 into e to the power of VGS minus VTH by VGS minus VTH divided by VT KT by Q. Okay. So, you have got this particular term now. I hope this is clear, that we have obtained from here, because we started off with that. So, recall here, let me put it once again here, VGS is equal to, we are seeing just below the threshold voltage by an amount equal to V. So, V is equal to VGS minus VT with threshold. Okay. Whether VTN or VTH, I call VTN sometimes because it is N channel, VTH is just straight away threshold voltage. So, that is the thing. And what is NN 0? Doping. NN 0 is carrier concentration here, that is doping. So, now what you will get is, when VGS is equal to VTN minus V, N 0 is equal to ND e to the power of minus V that. I have rewritten that, just putting NN 0 is ND. Okay. Therefore, current ID will be equal to QDN N 0 by LG. In fact, N 0 by NL divided by LG, and NL is equal to there. It is collecting all the electrons which are reaching there, like the collector of the junction. So, NL equal to 0. So, that is equal to okay. This I can write it as into area. I think everywhere I had left out area, whatever I was writing was current density, you multiply by the area. So, when I say current density is QDN, per unit area I have taken. So, if you multiply by the area, you get the actual current. So, this is equal to area into we are substituting for this quantity. Okay. So, that is this one. So, you have got this is equal to A into QDN divided by LG into e to the power of ND into e to the power of Vg minus V threshold by Vt. So, now you understand, I hope the idea is clear. The entire idea is that there is a current flow from the source to the drain, which is by diffusion. In the small thickness here, there is a current, and how much current flows depends upon what is the carrier concentration here is. How much is the carrier concentration depends how much is the drop here, from here to here is. More the drop here, less is the carrier concentration. Ideally, now from this equation, what will you say? Ideally, the first quantity here, that is what? Not ideally, this quantity that you have written here, that is Q A Q D N N D by L G. That is what we wrote initially at threshold voltage. Okay, this was equal to V threshold. So, that is the I naught. It is equivalent of I naught e to the power of I naught is actually the, or I 1 is the current at threshold voltage, which you may take it as 5 microampere, 10 microampere. Okay. So, from here what we can see is the drain current keeps on falling exponentially make VGS more and more negative. See, what we are talking of is this is a negative quantity minus V. So, you keep on increasing VGS negatively, that is more or less, this becomes less and less. So, when you go down to negative voltages of threshold voltage, below the threshold voltage, you have exponential fall in current. That is what you have seen here. That is what you see here. Okay. Now, there are several curves which are put depending upon the channel thickness, channel length. One thing, your threshold voltage itself is changes as you reduce the channel length. That we have seen, your two dimensional effect, the change in threshold voltage. Okay. Why should this slope change? You can see that the slope here is something, it becomes less sloping, it becomes flatter and flatter as you go to shorter and shorter channel lengths. The only way it can happen is, will be in this equation, this concentration here is changing. Okay. The concentration here is not falling as fast as you think it should be. From here, what is the change in voltage for 1 decade change in current? So, ultimately what we have got is I d is I d naught e to the power of V G S minus V T V threshold by V T. I am just getting cramped there. E to the power of V G S minus V T V threshold by V T. So, on a log scale, if you plot, on a log scale, logarithm to the base 10 I d log to the base I d naught plus V G S minus V threshold by V T 2.3. So, 2.3 times V T is 60 millivolts. So, ideally you should get a subthreshold slope, whether you talk of MOSFET or this MESFET, is that 60 millivolts per decade. When you, for example, if my threshold voltage is 0, I can reduce the current by 1 decade by just reducing the voltage by 60 millivolts. I can reduce the current by 5 decades down. Okay, it was 10 microamperes. I want to go to picoamperes, 10 to the power of minus 12, minus 6 to minus 12. That I can do by reducing the voltage 60 into 6, 360 millivolts, 0.36 volts. Now, notice what is happening here. Here we are talking of channels which are very, very short, and as you move from right to left, shorter and shorter. So, they are not falling by 60 millivolts. See, how many decades here? This is about 6 orders of magnitude down from here to here. 6 decades. These are all decades. 4, 10 to the power minus 4, minus 5, minus 6, minus 7, minus 8, minus 9. Okay. So, if you take 10 here, 10 minus 6 is 4 there. So, that is falling by 6 orders of magnitude. We expect in ideal case 0.36 volts, but notice how much it is. That is about 0 there, and this is about more than 0.5. It is not 0.36 or so, it is about 0.7 volts. So, what would say is, but still it is exponential because it is almost linear. So, the entire equation now gets modified with in short channel devices. This is long channel devices, subthreshold conduct. This is subthreshold current. Conduction in subthreshold region, there is gate voltage slightly below the threshold voltage. So, here in those devices, I d is equal to I d naught e to the power of V threshold divided by some constant N g times V t. where Ng is greater than 1. It is like the diode ideality factor, where N is equal to 1, it is 60 millivolts per decade. Now, here N is equal to 1, 2, 3, 4, depending upon how short the channel is. Long channel Ng is equal to 1, short channel is equal to 1, 2, 3, 4. You can see from these curves that we are given here, it could be very high. So, even when I went from 0 volts to 3 volts negative, the current has fallen just about 2 orders of magnitude. That you can see that N is maybe a factor of even 10, very large number. You are not able to turn off at all. What is the cause? The cause is this barrier is not remaining constant. As you go to shorter channel lengths, for the same voltage, let us plot and qualitatively discuss what is happening. Okay. So, this is the potential that I am plotting, and I am having that x equal to 0, x equal to Lg 1 long channel. Then I will have the potential coming down like this at a particular VGS, not like that. Up to that point, that is positive, 0, negative, positive, source to drain, the source and drain end. Same voltage, if I reduce the channel length, how will that be? If I reduce the channel length, this keeps on encroaching into this region, and with very short channel devices, what will happen will be, in fact, we are talking of very short channel devices, 1 micron, 1.3 micron. So, what would happen? That is there, this is long channel. And this is V, that is the voltage which is there below the threshold voltage. So, the barrier height here is totally controlled by the V. Okay? There is no other factor which is affecting the V barrier height. That means, the carrier concentration here is totally controlled by the V. Now, if I move this back short channels, what happens? Very short channel I put it here, Lg2 x. How will that be? That is, I am not able to plot it here, so I will keep it a bit more place for me. There, 0 Lg2. Lg2 is very much short compared to Lg1, 1 micron, half a micron of that order. So, the potential ideally what would expected would be start from here, whatever way it falls, okay, then come like this, then go up like that. But what is happening is, from the drain and the field lines terminate onto this, because it is so small, we are talking of 0.3, 0.4 microns. So, it comes instead of starting from here, the entire thing actually, let me just augment it and show you. Entire thing comes now like this, the potential varying like this, instead of varying like that, okay, the drain end also, that potential that we are talking of, that comes like this. It is actually a one dimensional effect here, whereas if the field lines coming from this side, when it is very short, they will encroach into that. So, the potential actually becomes like this. So, this VB, the barrier, is less than V. Okay. I am doing it very qualitatively, just to show you that it will no longer remain flat there, it will get, there will be current due to collection, due to not only diffusion, but drift also, one thing. Other thing is the electron concentration here is actually more, because the barrier is small compared to that. Because after all, the electron concentration at this end is equal, even if you take the diffusion equation, okay, you will have the electron concentration there is equal to doping concentration into e to the power of Vb by Vt minus. So, that Vb is smaller because of the two dimensional effect. So, put together it becomes less and less exponential, ideal, and you can see finally when you go to very short channel devices, what all we are talking of will never hold good. There will be barrier will be reduced quite a bit, there will be direct path from the nth region source to that particular end. That is almost what is happening here. Whatever we are talking of is will not hold good there. So, this is whatever we are talking will not apply there, but at least if this is not so much, okay, if encroachment is not too much, then still what you talk of holds good with that N g greater than 1. So, what we are telling is ultimately you have got, when you go to shorter channel lengths, the potential barrier at the source end to the transport of electrons towards the drain end keeps on reducing, or it is controlled by the drain also. So, for a given drain voltage you will have that factor N g greater than 1, and if you increase the V d, that barrier will further reduce. You will have another factor coming due to that V d. I am not talking about that. So, I just want to point out that the two dimensional effect harm the performance of the device. You go to shorter and shorter channel devices, one thing that happens is your threshold voltage changes. You may say, okay, I do not mind that much, but you will have to mind when you talk of integrated circuit. Okay. Other thing is you are not able to turn off your device so easily. You cannot turn off the device so easily, meaning you must apply much more voltage to turn off here compared to this device. So, shorter channel devices you get the two dimensional effect. In fact, this is what the N g that is plotted here. People have taken the slope of these lines exponential. How much is N g? You can see when it is 1.2 microns L g, okay, and the gap is 0.3 microns. Now, you can see the two effects are there. When the gap is 0.3, that is a bit larger, you have the short channel effect coming up, and you have got that factor is equal to about 2. What we have plotted here is for 0.15 micron gap. That is the worst situation. See what is happening. Go to shorter gate lengths, that factor is 10. The device that we are talking on the other side, its factor is 10. That is about, okay, that is a large number that you get. So, you get N g larger and larger in shorter channel devices, more and more difficult to turn off. Why is this difference between the two? Between this device and this device, it is almost the same gate length that we are talking of, but the channel length is smaller in this particular case. So, the two dimensional field in the direction when the gap is smaller, okay, if I plot it like this, n plus n plus n. So, source, drain, gate. So, this width if you reduce for same channel length, that is closer. So, when I apply voltage here, the field in this direction is more. So, when the gap between the gate and this channel is gate and the n plus region is reduced, the two dimensional effects become much more. As a result, you have got N g more, you have got threshold voltage more negative, all sorts of effects are there. How do you overcome that? So, this is summing up what I said now. Threshold voltage shifts in the negative direction, the short channel effects. Sub threshold slope, that I d versus log I d versus V g s becomes larger, and N g shows higher values. That coefficient, because it falls less steeply, it takes more voltage to turn off. Both effects are due to 2D field effect. Is it all right? Now, how to overcome that is, how can you reduce the short channel effect? The entire cause is the field in the vertical direction, that is 1D, then it is completely under your control. The moment other field also comes in, then the control of gate is reduced. It does not have as much control as you have earlier. That is why that N g factor comes. That is why the threshold voltage becomes more negative. You must apply more voltage. Okay. So, you must cut down the field in that direction for a given current. How can you cut down the field? Or You can cut down the field or increase the other field, both are same. You can increase the vertical field by increasing the doping, and of course, follow it up with the reduction thickness. This is a thumb rule. Scaling, you have to scale down the thickness of the channel, increase the doping. So, increasing ND in the channel adversely affects the mobility. You like to you prefer to increase the doping to reduce the short channel effect, but that affects your mobility. It will also affect your velocity overshoot effect, because after all it goes rises slowly. So, in a given time the peak velocity up to which it will go will be not as much as you expect. So, what is the solution? I think so. The high mobility and high electron concentration can be achieved using hetero structures. Now, you can see we are moving from the MESFET. So, that at this point we will stop discussing about the MESFET, the structure that we are discussing, but we move on to a device called high electron mobility transistor, because here it affects the mobility because you want high doping. What you require ultimately is high carrier concentration. For a given current flow, the field will be smaller if the carrier concentration is made high. J is equal to N into electric field, mobility into N into electric field into Q. So, if you increase N, field will be smaller. In the MESFET, to increase N, doping must be increased. So, that is the thing. If you use heterojunction transistor, what you do there is you actually cheat the donors in the sense you have a device where the ionized donors are located in one place and the electrons are located in a different portion of the device where the doping is not high. Okay. So, this is achieved by using heterojunctions. Since there is not much time left, I will just briefly mention what we are trying to do. We will go ahead with the heterojunction etc. tomorrow or next lecture. Okay. So, I do not want to take it up now, but few things I want to mention. What we mean, where the dopants are, where the electrons are. How it is done, of course, we will understand in the next couple of lectures. So, it is like this. We are now on to the 1980s or 90s or current which are going on in this device, real high speed devices. Okay. So, what you do is you have N layer or P layer, whatever it is, you have a layer here, let us put it as I layer, undoped. Okay. Now, you put a layer here which has the dopants, layer, doped layer, and D are the dopants. Now, this junction, what you make, if you make a heterojunction, what you mean by heterojunction is the band gap here is Eg1, band gap here is Eg2. If you do that, which we will illustrate, if you do that, supposing it is I or P, very lightly doped. You want it very lightly doped because when electrons are here, they do not experience that ionized impurity scattering. So, if you do that, what happens is the donors here will supply the electrons to this layer. Okay. How it is done we will see next, but this is exactly same thing what you do in the case of MOSFET. In the MOSFET, what do you have? You have an oxide, you have a gate. Here also you can put a gate if you want to control this charge. What do you do in the case of MOSFET? What is the energy band diagram in the case of MOSFET? P type substrate you take. MOS capacitor if you take. What is the energy band diagram? That is the conduction band of the oxide, valence band of the oxide. So, you will have energy band diagram like this. inverted region. Okay. You can see the electrons are locked here. You have a notch here. So, if you that is the inversion layer. Electrons somehow come here due to applied gate voltage, and they are locked here because they cannot climb up here. That is oxide. If you make a heterojunction, you will get a similar notch here. When you go from here to here, you will have a notch which will actually collect the electrons here, and those electrons come from the donor level. This is heavily doped donor, this is lightly doped. These electrons experience only lattice scattering. So, details of this heterostructure I will discuss in the next lecture. Okay. It is quite interesting part actually.